Assalamu alaikum students and welcome to lecture number 16 of CS317 operating systems. We are still working through the topic of concurrency and we use chapter 5 of the William Stallings book. In the last lecture, we explored the implementation of counting semaphores. We were introduced to one of the classical problems of synchronization, the producer-consumer problem and its versions. We implemented code for the producer-consumer problem using binary and counting semaphores. We were introduced to the concept of messages. So let us move forward with the same topic, message passing. Our first focus in message passing is on addressing. It is necessary to specify the destination of a message in the send primitive. Most implementations allow the receiving process to specify the source from which it wants to receive a message. The various schemes for specifying processes in send and receive primitives fall into two categories: direct addressing and indirect addressing. Direct addressing. With direct addressing, the send primitive includes a specific identifier of the destination process. The receive primitive can be handled in one of two ways. One possibility is that the process explicitly designates a sending process. Thus, the process must know ahead of time from which process a message is expected. This will often be effective for cooperating concurrent processes. Many times, it is impossible to specify the anticipated source process. An example is a printer server process which will accept a print request message from any other process. For such applications, a more effective approach is the use of implicit addressing. In this case, the source parameter of the receive primitive possesses a value returned when the receive operation has been performed. So when the receive primitive is called, the source parameter is empty, and once the receive operation is complete, its return value is placed in the source parameter. Indirect addressing. Messages are not sent directly from sender to receiver, but rather are sent to a shared data structure consisting of queues that can temporarily hold messages. Such queues are generally referred to as mailboxes. For two processes to communicate, one process sends a message to the appropriate mailbox and the other process picks up the message from the mailbox. By decoupling the sender and receiver, indirect addressing allows for greater flexibility in the use of messages. Sender-receiver relationships. The relationship between senders and receivers can be one-to-one, many-to-one, one-to-many, or many-to-many. One-to-one relationship. Only one sender sends to a mailbox. Only one receiver receives from the mailbox. A one-to-one relationship allows a private communication link to be set up between two processes. This insulates their interaction from erroneous interference from other processes. Many-to-one relationship. Many senders send to a mailbox. One receiver receives from the mailbox. A many-to-one relationship is useful for client-server interaction. One process provides service to several other processes. In this case, the mailbox is often referred to as a port. One-to-many relationship. One sender sends to a mailbox. Many receivers receive from the mailbox. The one-to-many relationship allows for one sender and multiple receivers. It is useful for applications where a message or some information is to be broadcast to a set of processes. Many-to-many relationship. Many senders send to a mailbox. Many receivers receive from the mailbox. A many-to-many relationship allows multiple server processes to provide concurrent service to multiple clients. Process mailbox association. The association of processes to mailboxes can be either static or dynamic. A one-to-one relationship is typically defined statically and permanently. A mailbox is associated with a sender process and a receiver process, and this assignment does not change throughout the lifetimes of the two processes. Ports are often statically associated with a process. That is, the port is created and assigned to the process permanently. Ports are permanently assigned to the receiver process. When there are many senders, the association of a sender to a mailbox may occur dynamically. Primitives such as connect and disconnect may be used for this purpose. In dynamic association, before a process issues a send or receive primitive, it needs to issue a connect primitive so that the operating system assigns a mailbox to it. Then it may send to the mailbox or it may receive from the mailbox. When the process has no need for the mailbox or when it wants to send or receive from another mailbox, it must issue a disconnect primitive so the OS can unlink it from its current mailbox. Mailbox ownership. A related issue has to do with the ownership of a mailbox. A port is typically created and owned by the receiving process. When the owner process of a mailbox is terminated, the mailbox is also destroyed. Some operating systems offer a create mailbox service, which can be called by a process, and in response, the operating system creates a mailbox. This service has two variations. The operating system may assign mailbox ownership to the process which calls create mailbox service. When the owner terminates, the mailbox is deallocated. The OS may assign mailbox ownership to itself. To destroy a mailbox, a process must request the operating system explicitly. The mailbox is not destroyed with any process. It remains as long as nobody asks for its deallocation. Message format. The format of the message depends on the objectives of the messaging facility and whether the facility runs on a single computer or on a distributed system. Some operating system designers prefer short, fixed length messages to minimize processing and storage overhead. If a large amount of data is to be passed, the data can be placed in a file and the message carries the file handle. A more flexible approach is to allow variable length messages. Variable length message format. The message is divided into two parts, a header which contains information about the message and a body which contains the actual contents of the message. The header may contain an identification of the source and intended destination of the message, a length field, and a type field to discriminate among various types of messages. There may also be additional control information, such as a pointer field so that a linked list of messages can be created, a sequence number to keep track of the number and order of messages passed between source and destination, and a priority field. Queuing discipline. The simplest queuing discipline is first in, first out, but this may not be sufficient if some messages are more urgent than others. An alternative is to allow the specifying of message priority. Different message types may have different priorities. The sender may designate priority levels to outgoing messages. We do a similar thing with emails when we classify them as normal or urgent. Another alternative is to allow the receiver to inspect the message queue and select which message to receive next. Here we show one way in which message passing can be used to enforce mutual exclusion. We assume the use of the blocking receive primitive and the non-blocking send primitive. A set of concurrent processes share a mailbox which can be used by all processes to send and receive. In the main program, a mailbox is created with the name box. The mailbox is initialized to contain a single message. There is no content in this message. It is referred to by the variable name null. The begin construct begins n processes in parallel, all requiring mutual exclusion over the same critical resource. The original figure lacks a closing curly bracket in the last line, so I have added it here. A process wishing to enter its critical section first attempts to receive a message. If the mailbox is empty, the process is blocked. Once a process has acquired the message, it performs its critical section and then places the message back into the mailbox. Thus, the message functions as a token that is passed from process to process. This solution assumes that if more than one processes perform the receive operation concurrently, then if there is a message, it is delivered to only one process and the others are blocked. If the message queue is empty, all processes are blocked. When a message is available, only one blocked process is activated and given the message. These assumptions are true of virtually all message passing facilities. Let us now do a simulation of the code that we just saw. The main program creates a mailbox. It places a null message in the box. It starts three processes in parallel, all of which issue blocking receive. Assume P1 to be the fastest. P1 receives the null message. All others are blocked. P1 enters critical section. When P1 leaves critical section, it sends a null message to box. P3 receives the null message. P2 is still blocked. P3 enters critical section. P1 loops back and issues blocking receive. When P3 leaves critical section, it sends a null message to box. P2 receives the null message. P1 is still blocked. P2 enters critical section. P3 loops back and issues blocking receive and gets blocked with P1, and so the code continues. Here is a solution to the bounded buffer producer-consumer problem. We take advantage of the fact that messages can be used to pass data in addition to signals. Take a look at the global variables. A constant integer capacity is initialized to the size of the buffer of the producer-consumer problem. A dummy message is initialized and is referred to by the variable name null. There is no need for the global integer I, so I have struck it out. Two mailboxes are used. In the main program, we call create mailbox twice to create them. One is called MayProduce and the other is called MayConsume. Initially, the mailbox MayProduce is filled with several null messages equal to the capacity of the buffer. The par-begin construct begins a producer and a consumer in parallel. The producer uses blocking receive to extract a dummy message from MayProduce. If it receives the message successfully, it generates a data item and puts it in a message called PMSG. Then it uses a non-blocking send to place PMSG in MayConsume mailbox. And obviously, if it does not receive a message, it remains blocked because it issued a blocking receive primitive. The consumer uses blocking receive to extract a message from MayConsume. If it receives the message successfully, it consumes the data item inside it. Then it uses a non-blocking send to place a dummy message in MayProduce mailbox. Again, if the consumer is not successful in receiving the message, it blocks because it issued a blocking receive primitive. If there is at least one message in MayConsume mailbox, the consumer can consume. Hence, MayConsume serves as the buffer. The data in the buffer are organized as a queue of messages. The number of messages in MayProduce shrinks with each production and grows with each consumption. This approach is quite flexible. There may be multiple producers and consumers as long as all have access to both mailboxes. The system may even be distributed with all producer processes and the MayProduce mailbox at one computer and all the consumer processes and the MayConsume mailbox at another computer. In dealing with the design of synchronization and concurrency mechanisms, it is useful to be able to relate the problem at hand to known problems and to be able to test any solution in terms of its ability to solve these known problems. Several problems appear frequently, both because they are examples of common design problems and because of their educational value. One such problem is the producer-consumer problem, which has already been explored. In this section, we look at another classic problem, the readers-writers problem. The readers-writers problem is defined as follows. There is a data area shared among a number of processes. The data area could be a file, a block of main memory, or even a bank of processor registers. There are a number of processes that only read the data area, or readers, and a number of processes that only write to the data area, or writers. The conditions that must be satisfied are as follows. Any number of readers may simultaneously read the file. Only one writer at a time may write to the file. If a writer is writing to the file, no reader may read it. Thus, readers are processes that are not required to exclude one another, and writers are processes that are required to exclude all other processes, readers and writers alike. Difference between readers-writers problem and mutual exclusion. In the general problem of enforcing mutual exclusion over a shared modifiable resource, all processes read and write the critical resource. In the readers-writers problem, readers do not also write to the data area, nor do writers read the data area while writing. For example, suppose that the shared area is a library catalog. Ordinary users of the library read the catalog to locate a book. One or more librarians update the catalog. If the general solution of enforcing mutual exclusion is used for the readers-writers problem, we will be serializing not only the accesses of the writers but also those of the readers. If we use the general solution of enforcing mutual exclusion on the library catalog, every access to the catalog would be treated as a critical section, and the readers would be forced to read the catalog one at a time. This would clearly impose delays. Readers do not modify the shared resource, so implementing mutual exclusion for them will make the system intolerably slow. Instead, we must focus on preventing writers from interfering with each other and preventing reading while writing is in progress. Difference between readers-writers problem and producer-consumer problem. Can the producer-consumer problem be considered simply a special case of the readers-writers problem with a single writer, the producer, and a single reader, the consumer? The answer is no. The producer is not just a writer. It must read cue pointers to determine where to write the next item, and it must determine if the buffer is full. Similarly, the consumer is not just a reader because it must adjust the cue pointers to show that it has removed a unit from the buffer. Let me deviate a bit to talk about resources. I promise you that I'll get back to the point. Anything that a process may ask for is a resource. There are two types of resources: reusable resources and consumable resources. A reusable resource can be safely used by one process at a time and it is not depleted by this use. A consumable resource is one that can be created and destroyed. When a process uses a consumable resource, it is depleted by this use. Suppose you and a friend come to my office. I offer the two of you a single cup of tea. If you drink the tea, your friend will not have any tea. If he drinks the tea, you cannot have it. So the tea in the cup is a consumable resource. When a consumable resource is used, it ceases to exist. That is why when you have drunk all the tea, the cup is empty and your friend is disgusted with you. Now consider the cup. I have only one cup in my office. When I am alone, I have tea in it. When a student comes in for a discussion, I wash the cup and pour some fresh tea in it for the student. The cup can be used by any one person at a time, but it can be washed and used again and again. The cup is a reusable resource. Also, nothing happens to the cup after I have had tea from it. It is just dirty and can be cleaned. Reusable resources are not changed by their usage. I must point out to you that the producer-consumer problem involves consumable resources. The consumer reads data from the buffer and then consumes it, or eats it, or destroys it. This is called destructive readout. Once the consumer has taken data from the buffer, we consider a buffer slot has become empty. So the data item in the buffer of the producer-consumer problem is depleted by use. In the readers-writers problem, there is a file and readers read it. They do not change it. If I read a file, it does not cease to exist after I have read it. It is not depleted by use. Writers change the file, but the existence of the file is constant. Whether it is read or written, it does not cease to exist by either being read or written. So if a scenario involves a consumable resource, it cannot be mapped to the reader's writer's problem because this problem does not involve consumable resources. There are two solutions to the reader's writer's problem. A solution in which readers have priority and one in which writers have priority. Readers have priority. If many readers and a writer arrive together, the readers are allowed access to the resource first. Writers have priority. If many readers and a writer arrive together, the writer is allowed access to the resource first. This figure is a solution to the reader's writer's problem using semaphores in which readers have priority. This shows one instance each of a reader and a writer. The solution does not change for multiple readers and writers. The global variables include an integer called read count, which keeps track of the readers in the system. Two semaphores are used. One is called X and the other is called WSIM. Both are initialized to 1. The main program initializes read count to 0. That is, when we begin, 0 readers are accessing the file. The par begin construct introduces a reader and a writer program into the pool of executable processes concurrently. The writer process is simple. The semaphore WSIM is used to enforce mutual exclusion. As long as one writer is accessing the shared data area, no other writers and no readers may access it. Please note that the last line in the critical section of the reader process is read count minus minus. I have corrected the figure in this video. In order to understand the reader process, let us first assume that this is the first reader in the system and that the file is not being accessed by any writer right now. The first reader does a sim wait on X and is not blocked. It increments read count to 1. It does a sim wait on WSIM and is not blocked. Now it can access the file. It signals on X and then starts reading. Assume a reader comes into the system. It does a sim wait on X and it is not blocked. It increments read count to 2. It signals on X and starts reading. Now a third reader can come in. When there is already at least one reader reading, subsequent readers need not wait before entering. The semaphore X is used to ensure that read count is updated properly. Read count is a global variable and for readers it is shared modifiable data. So it must be ensured that two readers do not update it together. The semaphore X implements mutual exclusion on read count. Now assume that the first reader comes in the system and that the file is not being accessed by any writer right now. The first reader does a sim wait on X and is not blocked. It increments read count to 1. It does a sim wait on WSIM and is not blocked. Now it can access the file. It signals on X and then starts reading. Assume a writer comes into the system. It does a sim wait on WSIM and is blocked as WSIM is -1. So we can note that the reader process also makes use of WSIM to enforce mutual exclusion. Every leaving reader decrements the read count variable, but the last reader additionally signals on WSIM. In this way, the last reader allows any blocked writer to unblock and access the file. Now I will conduct a parallel trace using multiple readers and writers for the code that we just saw. We begin with read count equal to 0, X equal to 1, WSIM equal to 1. Writer 1 comes into the system. It does a sim wait on WSIM, does not get blocked, so it starts writing on the file. Reader 1 comes into the system, does a sim wait on X, does not get blocked, so it increments read count. Reader 2 enters, does a sim wait on X, and gets blocked in its queue. X equals -1. Meanwhile, reader 1 sees that read count is 1, so it does a sim wait on WSIM. As a writer is already present, reader 1 gets blocked on WSIM. WSIM equals -1. Reader 3 enters, does a sim wait on X, and gets blocked in its queue behind reader 2. X equals -2. Writer 2 comes into the system. It does a sim wait on WSIM, gets blocked in its queue behind reader 1. WSIM equals -2. Writer 1 has finished its work, so it does a sim signal on WSIM, which unblocks reader 1. Here we see that the reader is being prioritized over a writer. Writer 1 leaves the system. Reader 1, who has freshly unblocked, goes on to its next line of code where it does a sim signal on X. This unblocks reader 2 from the queue of X. X equals -1. Two processes are active now, readers 1 and 2. Reader 1 starts reading the file. Reader 2, who has freshly unblocked, goes on to its next line of code where it increments read count. Then it does a sim signal on X. This unblocks reader 3 from the queue of X. X equals 0. Three processes are active now, readers 1, 2, and 3. Reader 2 starts reading the file. Reader 3, which has freshly unblocked, goes on to its next line of code where it increments read count. Then it does a sim signal on X. X equals 1. Reader 3 starts reading the file. Reader 1 has finished reading. It does a sim wait on X, does not get blocked. X becomes 0. Reader 1 moves on to the next line of code and decrements read count. Reader 2 has finished reading. It does a sim wait on X. As read count is being manipulated by reader 1 right now, reader 2 gets blocked in the queue of X. X equals -1. Reader 3 has finished reading. It does a sim wait on X. As read count is being manipulated by reader 1 right now, reader 3 gets blocked in the queue of X. X equals -2. There is only one active process in the system, reader 1. Reader 1 moves on to the next line of code. Read count is not 0, so it skips the body of the if and does a sim signal on X. Reader 2 gets unblocked. X equals -1. Reader 1 has left the system. Reader 2 is the only active process. Reader 2 moves on to the next line of code and decrements read count. Read count is not 0, so it skips the body of the if and does a sim signal on X. Reader 3 gets unblocked. X equals 0. Reader 2 has left the system. Reader 3 is the only active process. Reader 3 moves on to the next line of code and decrements read count. Read count is 0, so it moves into the body of the if and does a sim signal on WSIM. Writer 2 finally gets unblocked. WSIM is 0. Reader 3 does a sim signal on X. X equals 1. Reader 3 leaves the system. Now writer 2 is the only process running. In this solution, readers have priority. Once a single reader has begun to access the data area, it is possible for readers to retain control of the data area as long as there is at least one reader in the act of reading. Therefore, writers are subject to starvation. In this lecture, we explored inter-process communication using message passing. We learned how to use messages to enforce mutual exclusion. We learned how to use messages to solve the producer-consumer problem. And we explored the readers-writers problem. Before I leave you, I reiterate the same points. Read the book, do the parallel traces, try to get a clearer idea of how the code is working. Write your questions on a piece of paper and keep them with you when we meet in the online session. And if you have any suggestions relevant to the lecture, the content, or the presentation, I'm all ears. Write me an email. Take care of yourself. Allah Hafiz.